Hello everyone, welcome to lecture 28 of the online course on introduction to microwave and optical metamaterials. Today's lecture will continue our discussion on metallic nanostrips for magnetism. So, here is the lecture outline. We will continue the discussion on the pair of metallic strips as magnetic metamaterials that you have seen towards the end of the last lecture. We will see how we can have magnetism in the visible spectrum, and then we will develop an analytical model for those magnetic nanostrips that give us better idea of what we are doing. So, if you recall from the previous lecture, the basic structure of the nanostrip magnetic metamaterial basically consists of a pair of metallic strips. Here you can see the two, which is spaced by a dielectric layer. Here we are using alumina, okay, Al2O3. Now, the upper and lower strips are not identical, and that is why the overall cross section of the strip pair will look trapezoidal in shape. Now, the nanostrip structure exhibit both magnetic and electric resonances under TM polarization, where you see the magnetic field is basically polarized along the strip, right. Under T polarization, where the electric field is basically polarized along the strip, the structure shows no resonance effect. And we have seen that the fabrication of this can be achieved by electron beam lithography and vacuum deposition. So, here the figure shows the field emission scanning electron microscope, that is FESM, okay, image, and this is atomic force microscopy image of the fabricated structure of this paired nanostrips. Okay. Now, in this structure, when you calculate or when you characterize them and get the experimentally measured value of transmission, reflection and absorption, which are plotted here. Okay. So, this is absorption, okay, this is reflection, and this is the transmission. Okay. What you basically see here, that all done under TM polarization, because that is where you can excite those magnetic and electric resonances, and the resonances are marked as lambda m and lambda e. Now, if you want to understand the nature of this magnetic and electric resonances, it is also good to do simulations of the electromagnetic field using commercial software, something like COMSOL multiphysics, okay, that will allow you to see the field distribution at these two resonance wavelength, lambda m and lambda e, okay, and this is how they look like. So, here is basically the cross sectional view of this paired nanostrip, and the top one shows the electric resonance, the distribution of the electric displacement field at lambda e. Here you see the magnetic field distribution at the magnetic resonance wavelength of lambda m. Okay. So, you can clearly see this particular arrows show the electric displacement and the color map shows the magnetic field, right. So, the arrows are basically indicating the electric displacement and color map gives you the magnetic field intensity. That's something important to remember, right. Now, let us take one by one. So, in this particular case of B, where you are seeing the magnetic resonance, you can see that the electric displacement is predominantly aligned along one direction, right. Sorry, we are talking about this one, right. So, at the magnetic resonance at lambda m, that is in figure B, you can see that the electric displacement is basically forming a loop. Okay. So, that is a loop of the electric displacement current, and that results into a artificial magnetic moment, right. So, you will also see a strong magnetic field inside the loop between the two metallic strips. Now, if you go to the upper figure, that is corresponding to the electric resonance at lambda e wavelength. So, there you see that the electric displacement is predominantly aligned along only one direction, okay, with small circulating components. Okay. That means the magnetic field is much lower compared to the magnetic resonance here. The small circulating component of this electric displacement basically gives you small magnetic moment. Okay. However, this is much weaker And another important thing is to see that the minor loops that you can see from the arrows in the displacement basically give you magnetic anti-resonance. Okay. Now, during the first few years of the intense study of this kind of metamaterials, split ring resonators and their analogues have been the meta-atom of choice for this kind of magnetic metamaterials. Their magnetic response usually spanned over C-band microwave frequencies to even the end of the long wavelength end of the visible spectrum, right. Now, at visible wavelength, that is between 800 nanometer and 400 nanometer, okay, other structures like coupled nanorods or nanostrips were basically preferred, right. Split ring resonators could not go beyond that because of the saturation effect, which we have already discussed in the previous lecture, because this have their intrinsic limit, right. So, these coupled nanorods and nanostrips became popular. So, in this particular lecture, we will see a route to strong and controllable magnetic response in the visible wavelength range, mainly using structures like paired of thin silver strips, okay, that can give a strong tunable magnetic response within the visible spectrum. Now, before we proceed with discussing experimental demonstration of magnetism in the visible range, it is important to address one issue, that is regarding the constituent materials which are typically used in metal dielectric metamaterials that operates within the visible range, right. So, for metamaterials that are operational from microwave frequencies, okay, to near infrared, okay, but in the case of microwave frequencies, copper is the commonly used one, specifically for PCB based metamaterials, because they are easy to fabricate as well, okay, using the PCB fabrication. However, for the infrared band of the optical frequencies, both gold and silver structures are routinely used, of which gold is typically preferred owing to better performance in various nanofabrication techniques, and also it is more stable against environmental degradation such as oxidation and all. So, what are the challenges in the visible frequency range? Okay. So, if you want to design metamaterials at visible frequency, silver is ideal due to its smaller loss factor as compared to gold, but as we discussed that although gold is more stable, gold is found to be less suitable in terms of performance because it has got higher losses, typically 3 times larger losses as compared to silver. Moreover, the absorption edge of gold due to the interband transition from 5D to 6SP falls within the visible range, which essentially rules it out as a material of choice for metamaterials at the visible frequencies. Therefore, whenever people tried making metallic nanostrips which are supposed to operate in the visible range, silver was the choice of material to form the pair of metal strips. Now, as for the dielectric spacer between the silver nanostrips, okay, you have to choose a material with relatively large dielectric constant that can give you better field confinement, right. So, in the present structure, as you can see, alumina, which has got a refractive index more than 1.6, is preferred over silica, which has got a refractive index less than 1.5. And also note that semiconductors with high dielectric constants such as silicon and germanium should not be used for visible light metamaterials because of the substantial loss caused by electron transition across the band gap. Okay. So, now we move on to the discussion of the experimental demonstration of magnetism in visible frequency range using nanostrip pair samples. So, again these are silver nanostrips separated by alumina, okay, and we have seen this structure already. This nanostrip pair stack has a trapezoidal cross section, and these are the other dimensions. You have got a the silver layer thickness is 35 nanometer. The spacer has a thickness of 40 nanometer, okay, and then people have fabricated 6 different structures with varying width, okay. So, W has been changed on the same substrate and fabricated simultaneously for a fair comparison, okay. So, the 6 samples basically named here A to F. So, they have strip widths starting from 50 nanometer to 127 nanometer. So, A is the thinnest one and F is the widest one, okay. The transmission and reflection spectrum. So, this row is transmission, this row is reflection, and this left column is for TM polarization, the right column is for T polarization. So, this transmission and reflection spectrum of all the samples were measured to reveal the nature of the resonance qualitatively, right. So, what you can see that for the TM polarization, okay, you can see strong resonances getting observed, whereas for the T polarization there is no resonance. So, you are basically seeing non-resonant wavelength dependence over broad range, and the slopes, okay, of the spectra in the T mode basically tells you that the samples basically act like diluted metal in this case, and that could explain that the samples will look blue because you are having so much transmission in the blue regime. So, it will look blue in the transmission mode, and in the reflection mode they will look like red, okay. So, that you can observe from here. Now, the magnetic resonances that you can see in the TM polarization case basically occurs over a span of 491 to 7, you can see here this is the resonance. So, 754. So, typically from this graph you can see the resonance, okay. So, that basically covers most of the visible spectrum, which is very good, and it is important to note the position of the resonant wavelength in this TM mode, okay, and you can see that they basically move towards blue when decreasing the width of the strips from sample F to sample A, right. So, this basically confirms consistent magnetic resonance scaling property, which is a good indication, and that can serve as a guideline to develop other devices or meta atoms for this kind of magnetic responses within the visible range. The spectra for TM polarization. So, if you look into more carefully, okay, so the spectra for the TM polarization is shown here. It has got basically 3 distinctive characteristic features, okay. So, you can actually see that there is magnetic resonance, which is lambda m. So, again these 3 colors basically tell you about the blue is the transmission, the green is the absorption in this case, and this red is the reflectance. The dashed ones are basically simulation, the solid ones are basically experiment, okay. So, what you are doing, we just took one particular set from the previous slide, and we want to go into details and understand what are these peaks, what they represent. So, you can see for TM polarization you are seeing magnetic resonance. So, you are taking the spectra from TM polarization, you identify these peaks, what is happening here. So, you can see that the magnetic resonance basically shows that it is caused by antisymmetric current flow in the paired strips, you can see at the bottom strip the current is flowing this way, and in the upper strip it is flowing on the opposite direction. So, you basically have a loop forming up, and that is giving you the magnetic resonance. Okay. And this key resonance is very important for pursuing the nanostrip designs. Okay. Now, if you look into the second feature, which is the electric resonance, that is basically caused by a symmetric current mode. You can see in this case the currents are basically in the same direction. Okay. So, this electric resonance is coming from symmetric current flow, and it gives you a overall electric dipole effect. Okay. So, the spectral characteristics are like, these two resonances basically give you local minima in the transmission spectrum, okay, and they are appearing as maxima on the reflection spectrum, right. The absorption spectrum, which is here, okay, that also shows that the absorption is getting enhanced when you are close to these two resonance wavelength, and this is natural for plasmonic resonances in metal dielectric structure. Here the materials are plasmonic materials because you are using silver, and you can actually see those. So, once again, to summarize what you are seeing in the transmission, you are basically seeing two dips, one at lambda m, one at lambda e. In the reflection, you are seeing two maximum, local maxima, one at lambda m and lambda e, and then the absorption is also seen to get enhanced near those, because this is from the plasmonic resonance. Now, if you follow the transmission spectra, the blue one, it also displays a sharp turn back at relatively short wavelength, which is marked as lambda d. So, this characteristic wavelength basically indicates the diffraction threshold and serves as a fingerprint for such grating like structure. So, from here it will behave like a diffraction grating. Okay. So, for practical designs and application, it is desirable to have an analytical expression for the relation between the magnetic resonance wavelength lambda m and the geometric parameters such as w, d and t of this paired strip structure. Now, following the cavity model approach that we have discussed, okay, we see that for the range of parameters used in the experiments shown above, where you have lambda m greater than 2 n d w, okay, the resonance can be described by this. Okay. So, you can write epsilon m prime at lambda m. Epsilon m prime is basically the real part of the metal permittivity, okay, and n d is basically the refractive index of the dielectric spacer, okay, and the equation looks like this. So, you have epsilon m prime lambda d equals 1 minus n d square divided by t kappa times 1 plus cot h d kappa by 2, where kappa can be written as square root of pi by w whole square minus 2 pi n d divided by lambda m whole square, right. Now, because the fabricated structure are indeed more complicated than this kind of ideal cases that are described in the cavity model, there are small deviations from the lambda m which is calculated and the ones those are experimentally measured, right. And if you introduce some kind of a effective width, so such deviations can be completely accounted for. Okay. So, you have to introduce a new concept called effective strip width. So, you can call W effective. Okay. So, for the range of parameters which are used in the experiments, calculation shows that W effective is typically slightly smaller than the bottom width of the strip. Okay. So, you can consider W effective to be 0.96 times WB, okay, and that improves the accuracy between the simulation and the experimental results. Now, the equation basically lacks analytical solution, but it gives useful approximations in some cases, right. So, first order approximation for the hyperbolic cotangent function with this parameter d kappa by 2 much lesser than 1 can be incorporated to simplify this expression. In addition, the second term in the square root, okay, can be also neglected, assuming that this is much smaller as compared to lambda m. So, if you do this approximation, the permittivity of silver, that is epsilon m prime, can be modeled by Drude model only, and you can write epsilon m prime, a function of lambda, will be 5 minus lambda square by lambda p square, while lambda p square is 134.6 nanometer, that is basically the plasma wavelength of the silver. Now, in that case, using this kind of simplification, the approximate solution can be written as lambda m, which is square root of 4 plus nd square w divided by pi t plus 2 nd square w square divided by pi square t d times lambda p. So, you see the magnetic resonance is basically function of this dielectric spacer refractive index, width of the strip, okay, WB, that is appearing, okay, W is the average width, right, yeah, W is the width, you can say, width of the strip, and then you have the thickness, and you have the dielectric spacer thickness, and lambda p, which is the plasma wavelength of silver. Now, this approximation provides some physical insight and confirms the intuitive conclusion that scaling down the width of the strip will result in a shorter resonant wavelength lambda m, right. So, that is the first thing that you can see. Next, there is a less intuitive conclusion that by reducing the thickness T, okay, of the metallic strips will tend to give lambda m a redshift. Okay. So, if you go for thinner metallic thickness, you will get a redshift in lambda m, and that is observed in both simulations and theory. Another interesting observation can be approximation can be obtained if the dimensions of the coupled strips are relatively large. That is, if you can consider W square to be much larger than lambda p square and T d to be much larger than lambda p square, in that case, you know, d kappa by 2 will be much smaller than 1. So, in this particular limit, the resonance wavelength lambda m will become approximately equal to 2 ndw times 1 plus lambda square by 4 pi square T d, which can be approximated as this, okay, because this is also small. So, you can consider this as only 2 ndw, right. So, in this case or in this kind of approximation, the resonant wavelength is basically independent, as you can see, of the thickness T and the separation D, right, and it is only depending on the geometric parameter W. So, this limiting case basically accurately describes microwave magnetic media using paired metallic wires, where the resonant wavelength is solely dependent on the length of the wires. Okay. So, not surprisingly, the second approximation leads to a natural solution of for the basic mode of the electromagnetic cavity with a characteristic size of W. Now, the figure here basically shows the plot of this magnetic resonance wavelength lambda m with respect to the average width W of the strip, okay, of the trapezoidal shaped paired strip samples from both experiment and analytical approach. So, the square ones shows the experimental one, and the triangle ones shows the value from analytical ones. So, as you can see, the experimental and the analytical calculations are very close when you consider W effective to be equal to 0.96 WB, and they are giving you the same trend. So, as you keep on reducing the width, your lambda m is basically reducing. So, more or less you can play within the entire visible range by changing the width. right. So, these are the observations. So, if you list them, you can see that the results obtained from the analytical solutions by using this kind of simple equations matches very closely with those of the experiment. Okay. So, that basically confirms the validity of this kind of analytical tool for designing. Okay. So, what are the implications? The equations can reliably guide the fabrication of magnetic metamaterials for targeted optical wavelength. The figure also exhibits negligible saturation due to side scaling, which indicates that such structure is capable of producing optical magnetism even at shorter wavelengths. So, there is no sign of things getting saturated, right. That is a good thing. So, with that we understand that the strength of the magnetic response in this kind of paired metallic strips are finally quantified via needs to be quantified via their effective permeability, which is mu prime, right, near the magnetic resonance wavelength, which is lambda m. So, the effective permeability was retrieved using numerical simulations through homogenization technique. For each sample, the material property and the geometrical parameters used in the retrieval process guarantee good agreement between the simulation and the experimental broadband spectrum. So, here are the findings. So, the minimal values of the permeability, okay, for the 6 different samples of the coupled strips that we have discussed, A to F. A is the thinnest one and F is the widest one. Okay. So, here you can see the permittivity values. For F it is around minus 1.6, that is around dark red light of 750 nanometer wavelength, and for the thinnest sample you have it around 0.5, okay, plus 0.5, that is around blue wavelength, which is less than 500 nanometer. So, all samples basically showed permittivity which are very different to unity, and that is telling you about the artificial magnetism, and the two important corner values are noted here, which you have already discussed. So, you can get negative permeability as well, and you can get permeability very different to 1 at 2 different wavelengths just by changing the width of the metallic nanostrips. So, to conclude, you can say that for all the samples the magnetic resonance wavelength lambda m is at least 5 times larger than the strip width w. So, that basically tells you that the coupled strip samples can be regarded as 2-dimensional metamaterials at those wavelength of interest. Okay. The experimental and the numerical studies of these coupled nanostrips with varying dimensions have offered a universal structure to create optical magnetic response across the entire visible spectrum. The obtained dependence of the magnetic response and the resonance wavelength on the geometric parameters gives us a general recipe for designing such magnetic metamaterial at any particular optical frequency of interest. Okay. So, you can make targeted designs. Okay. Additionally, it is possible to tune the magnitude of the effective permeability that you saw in the previous slide. Okay. So, you can get mu prime based on your requirement just by changing the coverage percentage of the strip. Therefore, the coupled nanostrip structure can serve as a general building block for producing controllable optical magnetism for various practical applications. So, with that we conclude our lecture. So, if you have got any queries regarding this lecture, you can drop an email to this particular email address mentioning the course title and the lecture number on the subject line. Thank you.